Welcome back to Tailored Materials and Surfaces. So as we recall from last time, if we take a normal surface or a normal metal surface, it will have an oxide on the top of it, and it will have probably hydroxide on top of that. So this is aluminium, aluminium oxide, aluminium hydroxide, oxyhydroxide, and then we've got a layer of stuff on the top, which is typically organic material, water, layers of water physically absorbed to the surface, and maybe dust and metals and all kinds of things. So that's what we expect to be on there, and we're going to think today about how we're going to get that back off again, because we want to treat this surface now to put something on there, maybe a colored coating, maybe the next layer, maybe glue it to something, and whatever we use has to deal with all of these layers. It has to either get rid of them, or it has to attach to them and rely on their bonds to the next layer below to hold it all together. So if we attach to this organic and water, it might just pull out. If we attach to the oxide and it's not very well attached, then it will just fall off and we've got nowhere. So that's what we've got to do today. If I were to ask you, which we can't do in this offline version, the first thing that you would come up with would be heat it up. And obviously if we heat it up, we can get rid of the organic and water. Firstly, the water at slightly higher than 100 degrees. And then we can get rid of the organic. But if it's a normal metal surface, the oxide layer will get thicker because we will increase the mobility of the metal ion, so it will become much more reactive and it will be able to make a thicker oxide layer. H nu is light, so if we put light on there, we will be able to remove these layers as well. But if we start at long wave, obviously if we use a microwave, it's a metal, so very little will happen. It doesn't tend to absorb it. If we use longer waves than that even, we can heat up the metal. So if we can inductively heat the metal up, which you've possibly had in another course, and that will heat it up and cause things to get hot, but it's just the same as heating it up in an oven. If we shine infrared on it, it's talking a little bit closer to the surface because we're putting our heat in from the outside instead of from the inside, so that's a little bit more efficient. And we're then just effectively motivating these organic and water molecules to desorb, because they're only physically absorbed, they're only physisorbed to the surface, so the molecules are not bonded, they're just stuck on. If we go shorter, we get to light, and optical light, like visible light, is going to do not a super amount. Water is transparent in the visible region. Organics are usually transparent in the visible region, so we'll have to go a bit shorter. If we get down to ultraviolet, we can excite the molecules and break their bonds, which will be particularly useful for organics because then we can break them into smaller bits and get rid of them. But we have a problem. The problem is they're not very motivated to leave because they're still then small organic molecules, so they're going to stay stuck to our surface. And the third possibility is chemistry, so washing. Obviously, we're not going to be able to wash off very many of these things, depending on what we do, but we can remove water, which you may have done in the lab by washing with something that isn't water, that's miscible with water, but is easier to evaporate. Acetone is a typical example. Ethanol is a typical example. In these corona times, you wash your hands with a alcohol-containing solution, and what it's actually doing is it's mixing with the water. Alcohol is miscible with water. It's typically ethanol or isopropanol, and then it evaporates. And when it evaporates, it takes the water with it, which dries up both your skin and also any microorganisms and viruses that are living there, which messes with them. They don't like that. The bacteria die from being too dry. The viruses tend to just get broken open because of the non-polar component of the solubility. But if we just put oil on as a non-polar solvent, the water that is round the virus particles or the bacteria will protect them from the oil. So we need something that will dissolve in both to get rid of them. So a good solvent would be a medium chain alcohol or a branched alcohol or something that will then help to dissolve both water and non-aqueous things, so non-polar things. So if we go to an industrial process, we would typically wash our surface with something, with soap, with water, with organic solvents to get rid of some of this material. But that turns out to be bad for the environment. What are we going to do with all that dirty solvent? It turns out to be difficult to run, so maybe we should do something different. We can imagine what we would do if we want to wash a piece of glassware in the organic lab. What we typically do is we put it into a bath of isopropanol and sodium hydroxide. But why are we doing that? The first thing is the organics that might be on the surface, which will be fatty acids, and a fatty acid from our skin, for example, or from dead animals, will be a glycerol group, which is propane triol, propane 1,2,3 triol, sorry, looking at you, propane 1,2,3 triol, and the ester of it with a long chain acid. It will either have 3 on if it's fatty acid, or 2 on and a phosphate group if it's a phospholipid. That's why there's an R on it. And what we want to do is break that down. So effectively we want to saponify it to convert it into soap. It's the same process as you would do in your sink in the kitchen when you put too much stuff down there, like organic things. You would put in some drain cleaner, which is sodium hydroxide, and it will attack here, doing the reaction that we know from chemistry. So we will have an OH minus, oops, let's have it coming here, an OH minus that nucleophilically attacks in here, sending the electrons out onto the oxygen, and then they go back in and kick out this other OH effectively. So this is a deesterification, and we are removing it, converting this into the fatty acid, and because it's sodium hydroxide or potassium hydroxide, some kind of hydroxide solution, it also ionizes the acid, so we end up with this thing, O minus Na plus, for example, or potassium, and we end up with the counter with the other part, which is the alcohol, or the glycerol, or the phosphate. These are both much more soluble than the fatty acid was, and so then we can remove them from our surface. The other advantage of hydroxides is that they will ionize all of these acids, and they will help to remove metal ions. So coming back to heating it up or shining infrared on it, then, let's put a line through that, coming over to heating it in some way. We want to get our organic material and water to leave, and so we can help to promote that process by increasing the gain, the thermodynamic gain from losing it, which we can increase by increasing the entropy of things in the gas phase, which we can do by reducing the pressure. So if we take our sample and we put it into a chamber so that we can suck out the air, we can motivate the water to leave by having a vacuum, and that lowers the boiling point. And if we can lower the boiling point below room temperature, we don't have to heat it up at all. But typically, if it's the last layer of water on a polar surface like aluminium oxide or something, it will be hard to remove. It will be bound pretty strongly, so we're going to have to warm it up a little bit. And so we might put a light in there, and then we get on to vacuum technology. So if we're in a vacuum, first of all, the heat can't leave this very easily because there's no convection in a vacuum there, well, not so much, because there aren't very many molecules inside the chamber, so it can't lose heat as easily. It can radiate them, but it's being shone in the other direction, so it's going to have a net increase in temperature. Obviously the walls are going to be cooler because they're attached to outside, so they're going to be losing heat, but our sample will get hot quite quickly. Then the probability that a water will leave will go up, and the probability that a water will stick to it will go down because of the higher energy and the fact that we're sucking them away the whole time. We could fill it with an inert gas or nitrogen or something. So just dry air would do if we want to remove oxygen. If we want to remove water, dry air would be fine. And then we want to heat it up. And the interesting thing about the vacuum is it will get a lot hotter than we imagine it is because it's not losing heat very quickly. Obviously, if we're in a vacuum already, we can get our energy in different ways. So we don't just have the option of a resistive heater, although that's simple. We could use something else. So what if we take an argon ion, for example, an argon plus, and we accelerate it with a voltage towards our surface? Then we can knock out some water out of the surface, and we can do that purely ballistically. It's very similar to heating it up, but we're physically putting in the energy with a particle that has some advantages and some disadvantages. It's obviously a lot more energy in a smaller area, so we can get things off more easily, but it will cause more damage to our surface locally, and it will take a long time rather than globally heating it, because if we heat it all, we're heating the top and the bottom. If we shoot it with argon ions, it's only going to hit the top face. So we can do that. That will also affect organic compounds and will tend to break them up. We can even break bonds with this if we hit it hard enough. So this brings us to the next thing that we're going to have next time, which is plasmas. This is a plasma ball. You can see just about, I've had to turn the light off so that you can see it. You can see just about the little traces of plasma to my finger. I'll put it this way, you can see it better. It's coming from the AC emitter in the center to the outside, and you can see two different colors. That's important. We'll come to that in a moment. What we're actually doing is we're knocking electrons out of gas molecules in there to make things like our argon plus that we would then use to bombard our surface with. Put that down, get my light back. So this is a simple version of a plasma. We have two electrodes, one of them is positive and the other one is negative, and there's gas in our chamber. And I'm going to think about how we might light it. So if we look again at my plasma ball, you can just about see it without the light off. There's an electrode in the middle. There's an electrode on the outside, which is my hand, and it's AC. Otherwise it would be very dangerous and it wouldn't get through the glass very easily. Let me unplug that so I don't get a shock. So here we have a DC plasma, just to make it slightly more simple. And what we're trying to do is we're trying to make a gas. Let's have noble gas because it's slightly simpler. We've got a gas atom in there. So we've got an argon atom. And what we want to do is remove an electron from it, which is very difficult. So we need to shoot that out with an electron. So we need an electron coming from here, somewhere over here, maybe not from the electrode, let's have it from here, coming along, knocking out another electron. So these are all electrons. So it continues, it bounces off, and it knocks out another electron. They are then both attracted to the positive electrode, and the argon becomes then positive. Let me rub it out and make it positive. Let's just do that. Let's make time go on a little bit. So now this argon has become positive, and it's going to start accelerating towards the negative electrode. So that's what we want to happen. That's what we want to use in this process to hit our surface, and it's one of the things that can then go on. However, once we've made this positive, an electron can fall back in. So any old electron from here can fall back in and neutralize the charge, causing it to go back to 0. That will give out a photon, h nu typically, or several photons as it cascades in through the energy levels of the argon atom, of the argon ion, becoming an atom. Becoming an atom. That is the light that we see. So if we look at a typical light that I'll show you next time, it will have a gas of mercury vapor, so low pressure mercury inside, and as electrons cascade in, they give out photons of light, typically ultraviolet light. And that ultraviolet light is then used to either excite visible light, if we want to use it as a light, or to murder bacteria, or to clean our surface, if we want ultraviolet light to hit our surface. So that's one thing that can happen. But if it goes back in, it destroys this argon ion, and it's then not charged anymore. If this argon ion wangs into the surface, it will pick up an electron and it will also disappear. So what we need for our plasma, for our light to carry on, is for one of these electrons to hit another argon, preferably really close to this positive electrode, knock an electron off, and then it will set off in its way in this direction. And we want one of these argon ions to hit another argon and maybe knock an electron out so that it can head off in this direction. So we need things to go on. We need the electrons to hit another argon before they get to the positive electrode, or maybe the side, depending on what we've done to the side. And we need the argon ideally to hit something as well on the way, but not too much. We want them to get up enough velocity. So if we take the two extremes, at high pressure, the electron that comes out barely gets started. It's starting to be attracted towards this positive electrode, and it hits another atom or molecule, and then it slows down again. That's no good. We're going to really struggle. We're going to need a huge voltage to generate our discharge, and we see that with a normal atmospheric pressure. So with atmospheric pressure, it takes a very high voltage to cause a discharge, and it stops immediately. So you get one discharge, and then typically it stops. It's very hard to maintain a discharge in atmospheric pressure. It's a lot easier to maintain a discharge at low pressure because our electrons have longer to accelerate in before they hit something. However, if we reduce the pressure too much, our argon will hit nothing on its way and whack into the surface, which is fine, but the electron will also hit nothing, and then we get to a stage where there are no free electrons and no free ions in our gap in between the two electrodes, and so the plasma goes back off again. So we discover from simple logic that there will be a window of pressure where we can have a plasma easily, and if we go too high in pressure, it will be more difficult. We'll need more voltage. And if we go too low in pressure, it will also be more difficult. We'll need more voltage, and eventually we won't be able to do it at all in both cases. But what else can we do to make our plasma better? We could make the gap very small, which makes it easier to light because we need a certain voltage drop per unit distance rather than just total. So if we have a smaller gap, we can get it to work easier. We could also have AC instead of DC, so that when our electron moves along, it nearly gets to the electrode and then it starts to move back towards the other one. This won't happen very easily because electrons are very small, so they move very fast indeed, but we can help that by slowing it down. We'll do that in a moment. However, the ions that we have, the positive ions that we have, we will take a lot longer to get there. So instead of going and whacking into the surface, they will move towards it and slow down, which is exactly what happens with my plasma ball here. It's a high frequency discharge, high enough frequency anyway, that the ions inside don't reach the ends, and so they just oscillate where they are. The electrons do escape, probably, because it's not that high frequency, but that allows the pathway to stay conductive, and that allows it to stay at the same position, because otherwise, if the ions dissipated, then there will be no reason for the arc to stay where it was. So that's why it stays pretty much where it is in this case. If we put a magnet in, we can bend the path of the electron. We can't put a different set of electrodes in because that's just going to modify the field, but if we put a magnet in, we can bend the path of the electron because it's effectively a charge moving in a magnetic field. And so we have our left and right hand rule. We will bend it at 90 degrees to its motion and the magnetic field, and so it will tend to make the electron bend away, and obviously that's going to make it take longer to get to the electrode. It tends to spiral in if we have the right magnet, so we can put in a magnet and that will trap electrons close to this electrode. We can do that if we want to make plasma at lower gas density, so a lower pressure. We can have magnets in there to hold the electrons close to our electrode. But the next question is, how do we start it? So we've got it going, we can keep it going with magnets maybe, we can keep it going with the right pressure, we can keep it going by having a narrow gap, and then we can get a bit out of the pressure range. But how do we start it in the first place? What's going to happen? So this is a diagram of a fluorescent bulb, like the ones you would see in our work, so in your place of learning. They've got two electrodes that are attached to AC. So when the plasma is alight, the AC will cause discharge along the tube. They're typically made with mercury vapor. Even if you get one of those compact fluorescents, or the ones with the twisty-wisty like filaments inside, not filaments, the twisty-wisty tubes inside, they are much the same, they're just longer and bent. That causes a discharge between these two, and once it's going, it can keep going with AC. But we need a trick to start it. If we attach our AC and just wait, okay, there's a possibility that a cosmic ray will go through, or some radiation, something radioactive, or we could put a radioactive source inside, but that would make it difficult to dispose of if it had deliberate radioactive material inside, and it wouldn't be very reliable. So we need a way to get it to light. The first way that we could do is the old style way, where we have a capacitor that charges up and drops a very high voltage. So we have a circuit attached to here that flicks a very high voltage on, which will cause a discharge. It will just rip the electrons out of some of the atoms in our tube and make it conductive, which effectively is one way to light it. The other way that we can do it is we can get some electrons to come out of our metal electrodes at the ends, and we can do that by heating them up. So that's what this circuit is for. So in this case, I've drawn it in a way to make it simple. It's not always as simple as this. Typically these days there's a little block of electronics that does it all for you, and it does it much more efficiently, but this is a simple way of doing it just for demonstration purposes. So we've got our AC, and we deliberately lose some of the AC across a filament, so that's a resistor. I put in another resistor, otherwise it would just go through here, or it would just light on one end. We don't want that to happen. So we've got a big resistor here, small resistor here. This gets hot because we're effectively on every cycle, we're passing current through the resistor, through the filament here, heating it up. It's just like an old style light bulb that none of you will have seen, but that's how they used to work. They used to just be a wire and it gets hot. So we've got electricity that goes through a wire, gets it hot, it's passing to Earth, and the other end of the cycle it goes through here, through there, and passes to Earth. If these resistors are high enough, then we've still got AC across these two. So effectively if the combined resistance is high enough, but if we imagine this to be very high compared to the resistance of this, then it would work better. Then we wouldn't get a dull spot on the end. Obviously these days they're not like that. If you take one of these tubes out of its fitting, or you buy a new one, you will see it's got 2 pins in each end. There are 4 contacts per tube, and that's because of exactly this setup. So effectively we're making this hot, and we've got AC that we can theoretically put a pulse in to get it to light. So what are those 2 things will be? The pulse of AC is simple, and you can see that in old ones where the ballast or the electronics is faulty. They try to light and they stop again. Old tubes, they'll try to light, fail again, try to light, fail again, and that's because of this spiking that's going on. So the electronics is trying to start it. It depends on how it works. The old style was as comparatively simple electronics. The newer ones are all clever, but in this case it doesn't matter for the physics of what's going on in the tube. So to think about what's going on, I would like to introduce you to Plancks experiment, where we've got an electrode. It's negatively charged, so we've got a power supply. We're applying negative charge to this electrode, we're applying a positive charge to this electrode, and we put it in a vacuum. So this box is supposed to represent vacuum, there's nothing in there. Then we put a current meter in there to measure if any current is passing. So if we do that, we can, let me get a different color because this black is pretty shit. So if we do that, we can see that if this is our voltage and this is our current, we can see that nothing happens and then something happens. So there is a threshold voltage where, let's have it a bit steeper than that. Let's have it going up like that. So there's a threshold voltage where our electrode starts to lose electrons. Electrons come out, they go to the other electrode, so current flows, or appears to be flowing. So this is our current. That represents how difficult it is to get the electrons to escape from the metal. If we heat up the metal, we can bring this back. We can, so effectively we're giving the electrons more energy in a different way. Here we're giving it to them with an electric field, and if we do it with heat, we can give it to them with just heat. If we do the same experiment, but we apply a small voltage, or we apply just a little bit of voltage, and we shine so if we shine light onto this electrode, that's Planck's experiment. If we shine light onto this electrode, it matters what color it is. So the shorter the wavelength, 1 over lambda, the shorter the wavelength, the easier it is. So we get again a step, but in this case we get a big step. We get no electrons coming out if the light is too red, and we get electrons coming out if it's blue enough, and that's because the photon is coming in, knocking into an electron, and if it's got enough energy it can knock it out. So in the case of our electrode, what we want to do is get the electrons out more easily, and we're doing that by heating it up. We could also choose a material where this function, either in voltage or in wavelength, so let's change it back to voltage, where this energy that we have to put in to get the electrons out is comparatively low. We call this the work function. It's the amount of work that is required to extract an electron from the metal. And typically with light bulbs and other types of filaments, we do that with a rare earth element. So we put some erbium or something on the top. Cerium is quite good. We put some lanthanides onto the surface of our metal, and they behave as the last conductive part, and so they can emit electrons more easily. They have a lower work function than other metals that we would have. So if we look inside our compact fluorescent tube or a normal fluorescent tube, the filament in there is a tungsten filament because it's got a very high melting point that is coated with some salts of rare earth metals so that it has a lower work function, and then it's heated up so that we can extract electrons from it relatively easily, and that's what seeds our plasma. We don't have to do that, but that reduces, in this case, the amount of energy that we have to put in extra in the form of heat and in the form of electricity. Okay, that will do for today, because we're going to talk about different types of plasma next time. Probably I will show you some things in the lab. So I will take my camera into the lab probably tomorrow and do that. See you next time.